Okay guys, as we look at these equations here, what we're going to be doing is solving for x values, but x values that actually exist in the exponent. And so this is unlike anything we've ever had to solve before where, if we had something like this, it's really easy to just get x by itself. Or maybe if we had, something like this, we could at least set it equal to 0 and try to factor or use quadratic formula. In terms of solving exponential equations, it gets a little bit more difficult the moment that I say 2 to the x plus 1 becomes something like 8, One thing, though, fortunately, that makes it a little bit easier for us is this property called the one-to-one property of equality for exponentials. At least it'll look like this. But the one-to-one property of equality, and what the one-to-one property of equality states is, as long as two things that have the same basis and are identical looking, but have the same basis are equal, then these can be equal if and only if then their exponents are equal. And so as an example of when that might come in handy, something like I've written here, 2 to the x plus 1 equals 8, would be more solvable because what I would recognize is that, well, they both sides here don't have the same base, but they can be rewritten both as powers of 2. And so, for instance, here I could say 2 to the x plus 1, this is already written with a base of 2 here, but if I were to write the right side, I would say 8. I really recognize that that's 2 to the third power there. And so, I'm sorry, I'll put my 3 out here, but I get 2 to the third power. And so what I'm going to see here is that I get 2 to the x plus 1 is equal to 2 to the third. And this is only true if their bases are equal and also if their exponents are equal. So at this point, we could conclude that this must be true. And by subtracting 1 from both sides, we could see that we get x equals, in my particular case, 2. And this is very easy to check, as a matter of fact. We could always just go put our 2 back in for our x up here. And what we end up with is 2 to the 2 plus 1, which is 2 to the 3 here, really comes out to be 8. And 2 to the third is definitely 8. And so one thing that I want to do here before we kind of kick this off and use our one-to-one property of equality and write a set of steps is basically, let's write out some powers. And what I mean by this is just powers of 2, 3, and 4. These are kind of good things to know here. And so in terms of powers of 2, 3, and 4, we're just going to say that, and I'll squeeze this in here, 1, 2, 3, 4, 5, 6, 7, 8, and 9. We could just go up here. We say 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. We say 2 to the fourth is 16. 2 to the fifth is 32. I'm going to put a box around that one because that's a good one to memorize here. We get 2 to the sixth is therefore 64. 2 to the seventh is 128. This is 256. And then this would be 512. Now that's taking it pretty far down the line here. With our powers of 3, we're not going to go very far. We say 3. 3 to the second is 9. 3 to the third is 27. And we'll go one more. 3 to the fourth is 81. And then how about one more? 243 would be 3 to the fifth. And then powers of 4, we get 4 to the first, 4. 4 to the second is 16. 4 to the third is 64. And then 4 to the fourth is 256. Basically, I want to be able to recognize these numbers so that we can rewrite them having bases of 2, 3, and 4. So as we look at something like number 19, okay, it says, hey, let's go solve this here. We could do this if both sides have the same bases. And so we need to recognize, well, 3 and 27, what are they both powers of here? They're both powers of 3. And so because we can write them both as powers of 3, we'll write this as 3 to the power of x plus 1. Let me try my x again here. X plus 1 is equal to 3 to the power of 3. But saying this would be equivalent to saying, well, then therefore x plus 1 would have to equal 3. Since their two things are equal with the same basis, their exponents are equal. So we get an x value of 2 here. And this, of course, would be really easy to go back and check. Now, some of these that I want to look at, say like number 21, a little bit more elusive, we say, well, then what's their common base? Okay. So we say 32. Well, where did I recognize this number? I want you to always remember that 32 is a power of 2. As a matter of fact, I'm going to rewrite this right now as 2 and recognize that this is 2 to the fifth power. On the left side here, we say, well, is this a power of 2? Now, the interesting thing about this is that if we take 1/2, okay, 1/2, and I raise this to a negative 1 power, it switches back around and becomes 2 to the power of positive 1. That is to say that we get 1 to the negative 1 over 2 to the negative 1. But whenever you have a negative exponent, you move its base, okay, and its exponents become positive again. So really it's 2 to the 1 over 1 to the 1. What I would like to point out is that 1/2 is actually a power of 2. And so when we say, well, what power of 2 is this? We would say that if I were to take 2 to the negative 1, that would be the same thing as 1/2 to the positive 1. So now we have our powers of 2 here. What I want to do really quickly is simplify these. And whenever you raise a power to a power, we just multiply. We really get 2 to the negative x then is equal to 2 to the fifth. And so since we have equal bases now, this could be true if and only if negative x is actually equal to the 5, which would imply that x is actually equal to negative 5, and this would be something we could totally go verify. If we were to take 1/2 to the negative 5, 1/2 to the negative 5 is the same thing as its reciprocal to the positive 5. We can move those around, and 2 to the 5th is definitely equal to 32. So again, let's take a look at just maybe one more here, number 22. People say, well, you know, these aren't both powers of 4 sometimes to me. You know, 8's not a power of 4, 4 is a power of itself. But, you know, think about it this way. Well, maybe 4 and 8 have a common root. You know, they're both powers of something. And in this case, I recognize that 4 and 8 are both powers of 2. So again, we're going to rewrite this here as blank to the 2x, and we'll say blank to the x plus 1. But what you're going to see is we get 4 is 2 squared, and 8 is 2 cubed. And what we're going to do again is we're going to make sure we use our properties of exponents here. We're going to multiply. Okay, multiply times these. Okay, so we get 2 to the 2 times 2x is 2 to the 4x. On the right side, we get 2 to the 3x plus 3 times x plus 1, which really gives us 2 to the 3x plus 3. At this point, we could say then, hey, you know, these two exponents have to be equal because these two equal bases are equal. And the only way they can be true is if their exponents are equal. So 4x is equal to 3x plus 3. We just need to go and solve this guy now just by isolating x as we normally would. So we would get x equals 3, and this would be something good for you to go plug back in and check. So one-to-one property of equality, what I want you to do is rewrite both sides so that they have the same bases, and then we'll work with their exponents from then on. Cheers.